Hello everybody. We have this device here that is going to allow us to explore a bunch of the concepts that we've been looking at and how they interact with each other. So we're going to look at moment of inertia, energy, both rotational and the regular types of energy we talked about before, and also torque. So what this is a sort of a spool that I have this string attached to that when I pull on it is going to cause the entire thing to spin. And so I can attach a mass to this, and we can see that it will spin at a certain rate. So if I put a little 50-gram mass on there, and then we let this go, you can see that it spins about that fast, and it's continually accelerating as it goes, because as the object falls, you can either think of it as it's releasing energy, so its gravitational potential energy is decreasing as it falls, which means the kinetic energy of this needs to be constantly increasing, or in terms of torque. This is constantly getting pulled downwards, and if it's getting pulled downwards, that's applying a twisting force to the entire system, which causes it to spin faster and faster and faster. Now, one of the things we can change about this system is just the total amount of mass that we're hanging from it. And it should hopefully not be too surprising that if we increase the amount of mass, that will increase how quickly it spins and how quickly it's accelerating. So here I've got 100 grams. This is twice as much mass as before. We let this go. We can see it spins faster. And again, you can think of that either as there's more gravitational potential energy to convert into kinetic energy, or you can think of it as there being a significantly larger force able to provide a torque to twist the system and make it go faster and faster. And then we'll do one last one with 200 grams, so this is double again. And we should see that this goes even faster than before. Now, something else that we can change that's going to affect how fast it spins is the radius at which we are applying that force. I'm going to go back to my 50-gram mass. And we're now going to look at what happens if we apply this to different parts of the spool. So hopefully you can see on the camera there are 3 different layers here. Each one has a different radius. And so when the string is pulling on the back one, it's a larger spool, and so it's going to be pulling with a larger radius. So this is again what it looks like on this original one we were using with our 50 grams. And so if I let it go, that's how fast it rotates. Now, if I take and instead go to my second one here, this has a larger radius. The total amount of energy we have available has not changed in terms of the gravitational potential energy. But what we should see is that this winds up accelerating at a different rate. So I'm going to let this go, and we'll see that that spins a bit faster. And it should then hopefully not be too surprising if we go to the largest spool, which has the biggest radius. That is going to spin the absolute fastest. So I'm going to let this one go. See if we can get an even bigger acceleration there. And that difference is easiest to explain in terms of the torque. In each case, the force pulling down is the same, because we got the force of gravity on each one, but it's being applied to a different size radius. And so if I pull on this larger pulley here, since that has a bigger radius, my pull is going to be more efficient in terms of twisting it, which causes it to be able to twist the whole thing harder, which makes it accelerate. Its angular acceleration will be larger. That said, in each case, we still have the same total amount of energy available. And so as this falls from here down to here, its change in gravitational potential energy should be the same, which means that the total amount of kinetic energy that the entire system can gain should be the same. However, it'll just gain the energy a lot faster when we have our mass on the outside. Now, the one other thing that I can change is we can change, instead of how much mass we are pulling on it with, or how much mass or the radius we're pulling on it with, we can instead change the system itself. So I'm going to add some masses to this to change its moment of inertia. And so this is changing the effective mass of my entire spool. And so this should increase the moment of inertia of the spool itself, which means that when we are dropping that mass and converting its gravitational potential energy into kinetic energy, since this will have a larger moment of inertia, the same amount of kinetic energy won't cause it to spin as fast. Or if you want to think about it in terms of torque, we're applying the exact same force, the exact same torque, but to a larger moment of inertia. And since torque is equal to the moment of inertia times the angular acceleration, if we have a larger moment of inertia, we get a smaller angular acceleration. And so I'll put my 50 grams here on the outside. We'll see what that looks like. Slower than before. We can, without changing the mass of the system, of course I was able to increase this thing's moment of inertia by increasing its mass, but I can also change its moment of inertia just by redistributing that mass, and so that'll be the last thing we demonstrate. I'm just going to take these masses and move them to the outside. We know that the moment of inertia is based both on the amount of mass but also where the mass is, and as the mass gets further out, that causes the moment of inertia to increase. And so if I take all of these masses and put them on the very outside, this should give our system a significantly larger moment of inertia. And so if I put my same 50 gram mass on here now, we're going to see the smallest acceleration of all. Because although we have the same torque that we've had in a lot of other situations, we have our bigger moment of inertia, so we'll get a smaller angular acceleration. Or in terms of energy, although we're going to convert the same amount of energy as before into rotational kinetic energy, because this thing's moment of inertia is so much larger, its final angular velocity is going to be smaller, which means it's going to have a smaller total acceleration. So we'll let this go. We can see it's going, but now it's incredibly slow because the moment of inertia is so large. That said, we should, if we know the hanging mass, if we know the radius of whatever part the string is attached to, and we know enough information to calculate the moment of inertia of the spool or spindle itself, we should be able to mathematically figure out things like what is the final speed going to be, or how long is it going to take the mass to get to the bottom, acceleration, velocity, any of those quantities. And so that's going to be what we do next.